Hello. Yes. Hello. So before we get started, I asked a poll about, did you know about reactive programming? Some of you, there's someone amongst you that answered, I've never blocked in my life. Absolute legend. Love you. Cool. Do I start? Cool. So hello. Welcome. Welcome to the talk titled Reactive Java. Why are you here? Throughout the talk, I'm going to pace around the thingy, not because I'm nervous, not at all. It's for you to stretch your neck, because this is the last presentation of the day. So, reactive programming, what is it? Amongst all of the programming paradigms that we have, object-oriented, functional, reactive, I'm going to go out on a limb and say that reactive programming is the most well-known one of them. Even functional, which pains me to say. But reactive programming, a reactive paradigm, I think that is the most well-known and most used. And I'm going to back that claim in around 5 slides. So let's try and get a sense of what do we mean, or what I mean about reactive programming. In an imperative kind of world, think your normal C code, you can have A equals 10 and then B equals A plus 10. The mental model that we need to have is that variables are like sets of memory where we put things in, right? We have a slot in memory called A, and we put a 10 there. And afterwards, we're going to get A's value and put 25 in whatever B slot the operating system gives us, right? This is what the mental model of imperative programming we need to have. In contrast, in functional programming, when we say equals, we actually mean that is statement, not get the value and put in the memory, right? A is 10 and B is A plus 10. A is 50 makes absolutely no sense, like A was 10. And this is where immutability sort of might come from. But the idea is that the equal sign in functional programming means an is statement rather than a get the value and put it in somewhere in memory. With that in mind, reactive programming means when we assign A to 10, we mean that A is 10 now, and that B will be A plus 10 whenever, right? We can ask, what is A's value now? And we would get 10. And we could ask, after setting 8 to 50, what is A's value now? And we would get 50. And B's value would be 65. Cool. So you will realize throughout this talk that reactive programming has an underlying abstraction of time. We always query things on a time basis. We are always asking about variables when, and time is throughout all of the presentation. We're going to abuse annotation throughout these 100 slides that I have prepared for you. So whenever you see a squiggly lines, this means like the equals of a reactive world, right? We are assigning a value, we're assigning 10 to A now, and so on and so forth. So whenever we see squiggly lines, we think reactive. Cool. So, reactive. I'm backing my claim. Hopefully, you would get a sense that reactive programming is basically Excel, where we write functions, and when we change a value of, say, 50, then B's value is now 60. Right? It's always on the same time that we update one thing, and everything else propagates throughout our system. And that's the core competency of reactive programming and the reactive paradigm. And I'm pretty sure that we can all agree that Excel is much more used than either Java or Go or Haskell. Go and have you. So where does the idea of reactive programming comes from? Well, there's different historians put it in different ways, but the story that I want to tell you today is one in '97 by a paper called Functional Reactive Animation by Conan Elliott and Paul Hudek that have a key insight on what a functional, but what a reactive paradigm will entail, and this is the idea of a behavior. A behavior is something that, given a time, has a value. Right? You cannot get a value without a time. You always have to query it based on time. And that is the key abstraction based on this idea of reactive programming. And the time that I want you to think about is a real time. It's not a discrete number line. Right? Reals, unlike unicorns, which are famously not real, means that there's always a spot between any two numbers. And the time of a behavior that we ask about a value is in this continuous state. Examples of what a behavior might look like temperature. What is the temperature now in Barcelona? 150. What's the temperature tomorrow? Hopefully less. But temperature is an idea of a behavior, right? You ask what's the temperature now. Another, most likely more well-known to you folks, could be the idea of a behavior being the mouse position. Like, at any point, you can query, like, what is the mouse position? And the mouse will move around, and we can, with this behavior, think of, is the user hovering, or is the user clicking on the button and whatnot, right? The behavior is the idea of a value given a time. But, again, time as a functional reactive means in a continuous state. But the underlying computational model that we have is not. Right? You might have figured out right now that implementing a real number line is quite impossible. We can represent an arbitrary precision number, but not a real number. There's not enough computing memory in the universe to get that. And it's quite strange if you think about it, because von Neumann decided at some point that we should discretize everything, right? But the underlying idea that we have, the underlying physical phenomena that we have for our computing world are volts, or electricity. And electricity is, as real things, comes from a real place. But at some point, they decided, let's discretize everything into time slots or time chunks. Talk about premature optimization. Am I right? Jokes. Okay. So, how would one implement this kind of behavior like, right? We cannot represent anything that's real as in a real number line, so we need a way to compute these behaviors. One proposed alternative could be an idea of a clock system, where at any line of code that we write, you advance the clock. So currently, A is 10. We advance the clock. Now we have B being 25. Then we advance the clock, and we change both things at the same time, right? We change A to be 50, and now B to be 65. Every line of code updates all of our system. Hopefully, you will start pondering whether this is a good implementation, and I will tell you that no, it is not. Just for your sake, whenever there's text in the slide, I don't expect you to read it. There won't be any text. But things that can happen is, like, you have chaotic debugging. Whenever you try and debug something, every line of code changes your whole system. How can you debug that? Very difficult. Loops are very interesting to think about in a clockwise system. And the problems go on and on and on. So you usually don't implement a reactive programming paradigm or a reactive system in this idea of a clock, where every step of the way we update whole the system. But we could do something similar, right? We can do a reactive light approach, where when we assign with this reactive idea, right? We assign 50, we do the actual computation of, okay, A is now 50, and then we go into B and apply the new change. This is not updating the whole system, it's just updating the dependencies of any one thing that we change. I realize I'm going a bit fast. So a way that I like to think about it is that in this reactive world, this reactive declarative world, we are not writing variables and as the same way as we were writing in imperative, where we are saying to the program what to do, but rather we are explaining what the recipe is to create B, right? We explain that B is whatever A's value is plus 15. We're not doing the actual computation, but rather we are explaining to the system, whenever we query A, whenever we query B, go look at A's value and then add 15. If this sounds sort of similar to the semicolon in Java, or for comprehension, or do notation, or monads, you're right on track. That's exactly what I'm trying to get at. If any of these doesn't ring a bell, absolutely don't worry. You don't need this piece of information for the rest of the talk. So if you want to implement this idea of a reactive programming paradigm, light, right? When we change thing A, we also change thing B. This is not a new pattern, right? Famously, Gang of 4 implementation pattern. Anyway, there's a pattern called observable where they implement this kind of thing, right? When you change one thing, we change another. Just to get everyone up to the same standard, we'll do some coding or some slide coding. In the slides, everything compiles, so I'm not going to have any panic of things not compiling. So a bit of vocabulary that we use is, again, A and B are behaviors, things that change over time. We're going to call A an atom, being something that doesn't depend on anything. And we'll call B a derived value, right, being something that is derived from something else, in this case, A. How would one go in Java implementing this kind of thing, right? You can have this idea. Squiggly lines are much, much prettier than this sort of code, but the idea is, like, you have A that's an atom of 10, and we have a B that's a derived behavior from A, and it's whatever the value is plus 15. How would one go implementing this? Again, observer pattern means we have a class that has a value and something to listen. An atom is just the value. And the derived is quite interesting, but I know that is too small, so let's enhance. The derived value is, let's do two things. First, get whatever the value is right now, and create a new behavior out of it, like a new atom out of it. And when my dependent changes, set myself to the function application of the new value. What does this mean? In case where our function is get a number, add 15, our setting B to the new value of 15 would be this x plus 15. Just to go into the computation model, when we set A to 50, we would go to the set code that calls the listener and tells it, hey, propagate the change throughout. This will do the callback, where B is the function of the new value. The function is plus 15. The new value is 50, so we would get 65. So at this point, like, we have sort of implemented the observer pattern. If you want to go more into depth, you have the Gango 4. Please don't buy that book. I think it's online anywhere. But this idea of behavior of things changing over time means that we can build a whole vocabulary of things to do with things that change over time. If anyone has used Reactive Framework, if you're thinking operators, you're on the right track. We'll get onto those. But before I go over some of the newfound vocabulary, I will yeet you this quote by Alan Perlis that says that a language that doesn't affect the way that you think about programming is not worth knowing. Therefore, the reciprocal should be true, that if this programming paradigm changes the way that you think about programming, then maybe it's worth knowing about. So with this vocabulary of things that change over time, one of the things that we might want to implement is the idea of change things over time conditionally, like not always. This is a high-pass filter. I don't expect you to know about the electronics, because I don't. But the idea would be assign B to A plus 15, but only if A is more than 20, right? We guard this assignment. So whenever we assign A to 50, nothing happens, right? This is a thing that we can do on values that change over time. We can change over time, but how to implement this? Let's call it a filter. And this is the same thing, but the onChange part has a condition before it, right? So if the condition is met, A is more than 20, then do the setting. If not, don't do anything. There's a lot of other operators that we can do, again, with things that change over time. Think about, for example, pairwise. I want to get all the values, but get the last two values. Every time I'm going to get called, I'm going to get this new value and the old one, right? So I can calculate a delta, and I can calculate acceleration or speed if you're using positions. Other very useful thing to do when we have things that change over time is the idea of debouncing, right? Don't call me every time, but rather call me when there's no change in the next 10 seconds. These operators are very clear once you wrap your head around them, and it's a great way to wrap your head around them by looking at this Marvel's sort of implementation where you can change balls around and see how they operate. But just so we are all on the same page, right? If you see the pairwise top left corner, we have A and B, and when we get B, the resulting pairwise value is A, B, right? We got the last two. When we got the next C, we're going to get B plus C. right? So it's rolling average of the last two. There's debounce. There's a lot of other operators that we can implement. I am absolutely not going to implement any of these. These are left as an exercise for the reader. If you want to do it, go right ahead. But I'm going to tell you that there's already libraries that do this for us. For example, Rx has this very nifty implementation of these marvels where you can move things around and change and look at how the operators look like. And there's also other libraries available. At this point, maybe some of you are thinking, hold up, this looks really, really similarly to streams. But it's not. Not only because I had it in a red slide with a knot in front, but streams are meant to be synchronous ways of operating a big chunk of things. Right? Streams are, I have all these values, I want to parallelize them. I want to get the maximum value I want to get the maximum from all of these. Behaviors don't ever stop. They always are, they exist. As long as there's time, they will exist. We will not go over the idea of time being something that will ever stop because it's depressing. But streams means it's a full thing that you use once, and the idea behind it is you want to parallelize them. You want to parallelize it. Though there's many operators that look very similar to streams. But again, behaviors or reactive programming means a value that will change over time through forever. Right. So I'm very proud to have spoken about reactive without talking about threads. But at some point, we need to come up with, OK, now we know the idea behind reactive programming. What if I want to actually go and implement, right? The observer that we looked at in a few slides ago is nice and all, but it doesn't really scale. So talking in execution and going back to imperative, notice there's no squiggly lines and equals. We know in, again, C code, that each step gets executed one after the other, right? That's how normal imperative code works. In reactive, whenever we are changing A, we also need to do the recipe for B. Remember that as A changes, B changes, and I need to compute B at some point again. If B is an expensive computation, nothing there to do, right? Do the expensive computation. You cannot not do it. Although, maybe, if we never query B, we don't need to know what B value is, right? B is, again, a recipe on how to compute. It's not actually do the computation. If nothing queries it, then why do it? And this is taking the trees fall in the forest, nowhere around here doesn't make a sound kind of philosophy. And people in reactive world take that very seriously, where if there is no B, then there is no green. There is no expensive computation to be computed. If you're debouncing, then you don't need to do the query multiple times. You just need to do it at the end. It's very important that when we do things is at the last point that we can. We need to be lazy in this sort of scenario. Is that necessary for reactive programming? Absolutely not. It's quite useful for representing complex systems. Complex systems that look more like this than the previous slides, where we have a value that's fetching a user from a database somewhere, computing a hash that's very expensive in the CPU. We can audit things onto an audit file that we can maybe have a buffer or maybe go directly into the file, right? There's multiple implementations of it. But the idea is that every operation that we do is either I/O bound or something that is expensive on doing in memory, right? It's not going out and doing things somewhere different, right? Either a file or through the network. So how we will represent these kind of things moving forward is we'll have little dots and arrows where we have a value that needs to be computed first because both B and C depend on it. And how we'll manage these dependencies is having an arrow, a line to it, right? So B and C, both are an expensive or an I/O operation, depend on whatever A value is. But in real life, like these operations might come sooner or later, or halt, or panic, or what have you, right? So normal complex systems look more like this than silly three-dotted diagrams that I can show. And how we usually handle this in Java is by spooning a thread, right? I'm going to spun a thread and do whatever computation and block it. Then if I need it to wait for it, I'll join that thread and then join for the resulting value. And if at any point I'm waiting for someone to come back, then I'll just park the thread and wait for it. This is normal Java's behavior of doing things that depend on I/O or depend on depend on I/O. But threads, we realized, are expensive. How expensive? Well, you can span multiple hundreds, but there's a limit on how many threads you can have. So this means that any reasonably complex system that's spanning a thread for each I/O operation is going to be expensive, and we don't like expensive. So how do we tackle this sort of thing? Luckily, there's another well-known pattern called Reactor. And I know that Reactor is very similar to Reactive, so let's park the idea of Reactive for a while. And it's not Project Reactor itself, though Project Reactor obviously uses a Reactor. So let's do a bit of an experiment, right? Let's try and write our own server. Server that looks like reading from a socket, doing something, and then writing back to the socket. Think an Echo server, an HTTP server, whatever your Spring Web Flux application might do, right? Server, as is in our case, will be just these three blocks. So how would one go and implement one of these servers, right? Spanning a thread is while true, we repeat every so often, we accept a new connection, we handle it, and then go back to accepting a connection. How does the handling is this idea of I read from a socket, I do something, and I write out of the socket. So how does this look like, right? Client 1 comes in, I accept its connection, I run whatever the handler is, and at some point, I might get a client 2. When client 2 comes in, there's no one there to accept because my code is running client 1 handling procedure. So whenever client 1 finishes, I'm going to accept client 2, do its work, and then finish. Right? This is like single-threaded baby's first server. Luckily, we don't usually implement servers like this because we just said we are going to implement a thread per request kind of server, where I have a thread for every new client connection that I have, and I'm going to write a new thread and compute whatever the handler there needs me to do. How does that code look like? Again, I don't care about the actual code. It's just like we have an executors. That's the idea of a thread pool in some kind of way. And when I get a new connection, I accept it, and I dispatch it onto a new thread. And then I go back to accepting. Right? There's a main thread that's only accepting and dispatching, accepting and dispatching. How does that look like? Right? We have client 1. I'm going to accept it. And in thread 1, I'm going to start running the handling operation. At some point, I'm going to get client 2. Client 2 is going to get accepted, and then going to thread 2's operation. This is much smaller of a diagram than the first one, right? We have parallelized both handlings. So this is much better. But again, remember, threads are expensive. So expensive, in fact, that in 1990, there was this idea of the 10,000 connections problem, where there were starting to have servers that were trying to handle more than 10,000 connections. And you cannot spin up more than 10,000 threads, or at least in that day and age. And they coined a term for it, right? As I even saw stamps of C10K solved or C10K approved of servers that could, like computing power that could handle more than 10,000 connections. More so, WhatsApp famously in 2012 mentioned that 1 million is so 2011. Like by 2012, they were handling more than 2 million TCP connections. I don't have current numbers of WhatsApp, but I'm going to guess that's higher than that, given that most likely everyone uses WhatsApp nowadays. So handling a lot of connections simultaneously, threads don't do. So we need to write something that is, in some way, able to handle this sort of problem. So let's try and build that, right? We're going to call it Reacti, Nothing similar to Netty, don't worry. No lawyers will ever come from Netty telling me that it's too similar. And the core idea behind the Reactor pattern, or Reacti or Netty, is this idea of the synchronous event demultiplexer. I love the word. But it is a very strange word, but it does explain what it does. So let's go over it. So think of, what if we don't spun a single thread, and we are going to do all the computation in a single thread, but we have something that can listen to multiple things, right? The idea of synchronously, one thread, look at multiple demultiplex events. So how could that look like? When we get red's handling, right? The red client comes in, we synchronously event in the multiplex. Now it's a verb, and we handle it. At some point, whilst handling red, we might have come up with yellow. Like yellow's client starts, reaches us. But we have just one thread. We cannot compute yellow. But when red when red finishes, we again go to the synchronous event demultiplexer, and we ask the demultiplexer, hey, is anything there for me to do? And, well, yes, there's yellow. So I start writing yellow. Maybe after yellow, there's nothing to do, so the thread is waiting. And eventually, green comes in, and we do whatever green's computation means, right? So we're going to do it on a single synchronous thread, but the key inside here is that we can look at all of the things that are currently waiting for us and get the first one of this. If by synchronous event demultiplexer, I haven't convinced you that this is the best word that you've learned this 8 hours, this is basically an event loop. Like if you are into JavaScript development, this is the event loop. But event loop is much sillier term than the synchronous event demultiplexer. So how would that look like? Code-wise, I'm not even going to bother on how to write it. It's like 11 lines of code. I'm not going to do it. But the idea is that we have an acceptor somewhere, and there's a selector magic that tells us which one thing to do. So we have client 1. We start with the reactor, the single-threaded reactor, and we start handling it. At some point, client 2 comes in. We put in sort of like in a virtual queue of, hey, I need to do something with client 2. Whenever client 1 finishes, I do the demultiplexing. I see that there's something in the queue, so I pick up from the queue the client 2, and I do clients 2 work, right? So now it's exactly the same as we had in the. It's exactly the same that we had in the single-threaded application, and it's even worse, right? We have the red one there. But the key inside, and why I'm talking about Reactor in a reactive paradigm or in Reactive Java, is that our socket handling up until this point was written with equal signs. What if I go out of my way and write the handler with the reactive equal signs, right? The squiggly lines. So in this case, we can think about reading and writing our I/O operations. Like I don't actually need to do something. I just need to know when it is done. So in this scenario where we have a reactor and my handler is being split between reading and writing, when client 1 and client 2 come in, I put in a queue, I'm going to read from 1 and read from 2. I'm not doing any work in the reactor thread. I'm just waiting for the reads to be finished. At some point, the reading from the socket finishes, right? I got all of the HTTP text. So my reactor, right? This is the first blue thingy. So the reactor says, OK, now I can process 1, because I already have whatever it was in that socket. So I can do number 1. Number 1 finishes, right? The white part on number 1 finishes, and I can start doing the write. And again, I'm not doing the actual writing. I'm putting in a queue of, hey, operating system, write to the socket, whatever that is, and call me when you are done. Read 2 eventually finishes, so the reactor picks from the queue. It does whatever the do something in 2 is. We start writing onto 2. At some point, we stopped writing onto 1, so client 1 is done. And now eventually, write 2 is done, so client 2 is done. So this looks very similar to the idea of the multi-threaded application, right? It is shorter. We had just the one thread. So this one scales, not the other one. How to implement this? Again, Java is like 11 lines of code, but if you were to do it in more lenient programming language, one would call this either select or poll or epoll. These are all flavors of the same idea of a demultiplexer of sorts or a reactor pattern in some way. But there's no silver bullets. Even D&D knows that there's no silver bullets. So this is not an end-all, be-all solution. What happens if our do something is expensive, right? If our do something is expensive, we got client 1, client 2, we read, we got the read from the queue, and we do the expensive thing, right? There's nothing else to do but doing the expensive thing. Then there's the reactor part, right? Doing the, who should I listen? Oh, there's client 2, I need to do it. And then I start doing things in client 2. So now, if the do something is very big, we are back again to a single-threaded kind of experience. Even, again, worse, the selecting part is really expensive. So having that there is very annoying. So the synchronous event demultiplexer, last time, promise that this is last time I'm going to say the word, but the key insight is that this is not something that always works. It only works if inside our do something, we keep doing the same thing that we have done, right? We had a big chunk of things and the handler, and that was painful. So we are going to split the do something into multiple small things. Some of them, right, the yellow part could be doing actual computational work, right, calculating a hash, what have you, that needs to be done in a thread. But maybe there's other things that might be done in a different thread. And in the reactive world, it's very easy to explain to the program, do this after this, right? And what we are actually doing by writing the do something is not line after line what we need to do, is rather do yellow, then do red, then do blue, and whatnot. So in this scenario, we can start with yellows too, far before we finish doing all the client 1's work. And this is very similar to the multi-threaded application, as long as we have a lot of I/O and we don't have a lot of compute. So key takeaway is that reactive programming and the way of writing reactive programming for a web server, which is something that many of you might have done, you need to go all the way. You cannot have a reactive framework of doing server, but then write all your computation code synchronously in an object-oriented kind of paradigm. We need to go reactive all the way. We need to avoid this idea of having a big chunk of computation that cannot be split into smaller chunks. So let's not use Reacti because A, I didn't show you Reacti code, and B, it's horrible reading code. We can go over that code if you want. It's absolutely hideous. So don't use Reacti. There's a myriad of other things, other frameworks that implement this idea of a reactor pattern. There's namely Netty, which is most likely the most wide known. There's Webflux. There's Vertex. That's Ratpack. There's Undertow. By doing this, looking at what are the frameworks that exist, I realized that they're actually all using Netty. So use whatever you want. I personally prefer Netty. So first key takeaway of reactive programming and reactive programming in the web is that we need to do reactive all the way. Otherwise, it's worse performance than only using one thread. And nobody in their right mind would use one thread. So we talked about Reacti and web servers, right? And we paused the idea of reactive paradigm. So let's pick up that pin from the reactive and talk about a second problem that you might encounter while doing reactive paradigm work. Remember how we said that B is a recipe of how to do things, right? It's not actually doing the thing. And if we never query B, then good riddance. We don't need to do the expensive thing. But what happens if B panics, right? If B throws an exception, if B whatever. In imperative code, A would never be assigned, right? If we panic at some function, then the rest of the lines of code don't happen. In reactive, we're not panicking right there. We're panicking somewhere very far away from A being equal to 50. And we might need that A never reaches 50, right? I don't know, normal example of an account balance that you take money out and you put money in and you need to do both things in that transaction, whatnot. So there's times where we need to panic at a specific point in time, and we cannot allow it to panic whenever it wants. Just to drill this idea home, imagine that we have this Java code of a thread that the only thing that it's doing is running if the inner value that's being passed as a constructor is equal to 42. And we have a function that creates a new thread and starts that thread. But it starts the thread with A being null. You might have guessed this throws a new null pointer exception, right? We are trying to equals to a null. Cool. JVM does throw this null pointer exception, and it even tells you, hey, in this inner, there's a problem. But notice that the caller, the bug in our system is in the caller function. The A equals null, that's the problem part. It's not when it was executed that we care about. We cared about when we created the object. But there's no reference to it, right? Because stack traces in Java and in most applications are actually thread traces, right? When you start a thread, you get all the context, and the stack trace that you can have is just that context. So debugging in a threaded world is quite difficult. Luckily, we do have thread local variables where we can create threads and assign some values that are bound to it. We can put names to threads, so we know either if Netty is exploding or our application code is exploding or our task system is exploding. We have some experience in writing code that deals with multi-threaded applications. Think MDC, if you will. But in this hellhole, we have a single thread. So there's absolutely no way that we can know about the stack trace. Like, the stack trace means absolutely nothing. The stack trace is Reactor's Reactor land place, right? We could implement, if you think about in the same thread, we were doing the yellow C1 and then the yellow C2 in the same thread. So there's no way that we can get the context out of the thread, because the Reactor pattern is constantly switching of tasks, if you want, but not threads. So stack traces don't help at all. So key takeaway number 2, debugging a reactive application is hella hard. You don't have any context whatsoever. You need to, whatever context that you have, you implement it yourself, and you can go very wrong implementing some idea of a context-aware reactive in a reactive language. So be very careful on writing reactive code that debugging starts being very, very painful. Luckily, there are some proposals around JEP 453 about structured concurrency and some ways to having maybe the same thread capture different scopes or having hierarchies. The reactive libraries that we will mention in a bit all have some way of traceability and some way to recover failure, but it is by no means a simple task to tackle. So now I gave you an idea of what reactive programming means, how we can use it, why we want to use it, right? If we want to scale something up, it's very interesting to use, and two very poignant problems that we have by writing reactive programming applications. So with that newfound knowledge, let's dive into the world of reactive in Java. So in Java, we have a couple of libraries that we can use, namely Reactor, Rx, Java, and Aka are most likely the most useful ones. They all have this idea of a behavior, but nobody calls it behavior because, God riddance, if we're going to use a Haskell paper to write Java code, but the idea is the same, right? It's a value that changes over time. Maybe the value changes over time once, or maybe the value changes over time all the time. No matter. We can implement our own. Readers, if anyone wants to implement the idea of a completable future that returns a value and a next completable future, very interesting system that you can work out. But one of these is very dissimilar to the others, right? Both Flux Mono, Observable, Single Source, Sync, and Flow means a behavior. But Publisher, Subscriber, Subscription, and Processor, the Java 9 Flow one, do not mean behavior. They are by no means a behavior. The way that I like to put it is that our squiggly lines represented both the ability to do reactive code and also the operators that we have. Think pairwise, think filter, think combining things. With Java 9, we lose all of the operators. We are not talking about behaviors. Now, we are going to have a way to interop between different Rx libraries. That's the whole reason for flows in Java 9 interface. If you want to look at them, let's take a publisher, for example. Publisher has a single method that called subscribe that you pass in an object, and that object has a couple of callbacks of what to do when I subscribe, what to do on the next value, what to do on an error, and what to do when I complete. But this interface comes from the reactive streams, and this is a minimal set of interfaces. This is, again, by no means something that you as a user of a reactive language should be using. This is meant for interoperability. Do not use them. Because with this one method functional interface comes laws. If you ever saw a semigroup, an idea of an object that can be combined with another object and gives you the same type of object, right? That's called a semigroup. But the semigroup has laws that need to abide for it to be useful, right? Not any one object that can combine with other is a semigroup. It's only a semigroup if we have the law of associativity. And it's important to have associativity to do a myriad of other things. The same way, the publisher has laws. The problem is that the laws are like 20 laws. They're incomprehensible to a human being, at least for me. And they need to be, you need to abide by them to actually implement them and use them in a reactive world. Luckily, the people on Reactive Streams do have the TCK, the Technology Compatibility Kit, which is a framework of tests. So if you want to implement your own, you need to run these tests to realize if your flows implementation are actually law-abiding. Absolutely don't do it. Like Rx, Java, web flags, and whatnot, they all do. Don't worry about it. If you are very interested in doing it, you will waste a weekend of your time. Do with it as you wish. So these whole problems that we were looking at, right, of scalability, of threads and whatnot, started with a key premise that I never proved. That we said that threads are expensive. With Loom out of the way, maybe that's not a premise that needs to be considered anymore. So maybe reactive programming could go out the window with a Loom and virtual threads being good. I think that there's a talk tomorrow at 10 about virtual threads. Might be interesting to go. So what did we cover? We covered the idea of a reactive paradigm, a behavior, a value that changes over time. We talked about the computational constraints of our world and von Neumann's decision to do it that way, and how we can implement things around it. We built our own netty, which, again, don't use actual netty. We looked at two very, very distinct problems that reactive programming has. Let's remind ourselves. The first one is that if you don't go reactive all the way, the performance is even worse than using one single thread. And the second problem that we have is like debugging and traceability is very hard in the reactive world. We sort of looked at Java Flow. But if you want to look more into it, I will very much encourage you to look at Project Loom, right? The idea of virtual threads. Maybe threads are not expensive anymore. We briefly touched about this idea of structured concurrency, right? Writing concurrent code that sort of resumes in a orderly fashion that could be leveraged by reactive libraries and reactive frameworks. JEP 4.5.3 is not mainstream yet because they have some problems, but it's interesting to look at. We have not covered back pressure, and I am not going to cover back pressure on the idea of reactive programming in 50 minutes. But if you're interested in it, we can certainly talk about that later. And we covered just 3 operators, right? Debounce, pairwise, and filter. There's a lot of things that we can do with values that change over time. We can sample, we can debounce, we already covered, but there's a lot of things. So I highly encourage you to go to RX Marvel because, again, it's interactive, and playing with the marvels is quite fun, or at least that's my definition of fun. So without that out of the way, and with 6 minutes on the clock, thank you also very much for listening to me. My name was Joaquin, and that was Reactive Java.